All right, we have 2 days more to review. We're just going to run through a series of problems. So if you guys can turn to page 2, let's do a application problem for mean value theorem and average rate of change. All right, let's go ahead and read this problem here. An object's position is given by f of t equals 2 secant cubed of t over 6. It's continuous differentiable in our domain. Find the average velocity, average rate of change from 0 to 2 pi. So basically, this is just finding slope, right? Average rate of change is just slope between endpoints. So let's just go ahead and find our ordered pairs. And then this is going to lead into something where it's MBT related, but part A first. Okay, I just like to go ahead and rewrite it in a different form, even if we're not asking for a derivative. Sometimes that exponent in that shorthand form can be a little confusing in terms of how we simplify or how we evaluate an expression or a value. So I'm going to go ahead and just rewrite that cube, and also that'll be good for us to have it outside set of brackets to get ready for future derivative step. Okay, so to find average velocity, which is average rate of change, we're just going to find our ordered pairs and the slope. All right, 0 over 6, same thing as 0, right? Secant of 0. Let's just think in terms of cosine first, right? What's cosine of 0? 1, right? So therefore, secant of 0 will also be 1 because, right, cosine is 1, then secant will also be 1. So I can make this 2 times 1 cubed, which is 2. All right, let's find f of 2 pi. Right, secant of this reduces to be pi over 3, right? Secant of pi over 3. Let's think in terms of something that feels more familiar. What's cosine of pi over 3? 1/2. So the reciprocal must be what? 2, right? Okay, so we know cosine of pi over 3 is 1/2. So therefore, secant of pi over 3 will be the reciprocal of 1/2, which is 2. Right, 8 times 2 is 16. So our average velocity, or in other words, x. Average rate of change. It's just the slope between the endpoints. So change in y over the change in x. What does this reduce to be here? Is it 7 pi? Can I say this? 7 over pi. Sometimes I just want to make sure that we understand the common mistake that students make is we forget that pi has stayed in the denominator, and sometimes we just let it come up to the top, but this is not the same thing. Okay, so make sure that we understand that we can reduce the step 14 to 2, but that pi is not going to go anywhere. Part B says, at what point does the instantaneous velocity equal the average velocity? And if I reword it, that's basically saying, when is the instantaneous rate of change equal the average rate of change? That's really just an application of what? What do we call, what theorem is that called when we set the instantaneous rate of change equal to the average rate of change? Mean value theorem. Yep, that's just f prime of c equal to f of b minus f of a over b minus a, right? We have this part, we have the average rate of change. We just have to figure out the instantaneous rate of change. Now, part B is just asking you to set the equation up. We're not going to solve it, but we're going to do the instantaneous rate of change, which means we're going to find the derivative. To find the derivative, guess what rule we have to involve here? Chain rule. Yep. So set everything up here to chain rule. Got the outside and the inside portions that you're involving. If it helps, you may want to rewrite this t over 6 as 1/6 t, if it helps. If not, and that's fine. I want to make sure that we know it's just going to be power rule in there when we get to the u prime. Okay, so let's do chain rule here. Kind of a quiz review here, right? Quiz topic review. Okay, outside's derivative. 6 bracket squared. All right, let's secant u's derivative. Secant u, tangent u, times u prime was derivative of 1/6 t. Is 1/6. All right, basically just going to set these equal to each other, this equal to 7 over pi. I'm going to just do a little bit of cleanup here. Looks like the 6 and 1/6 can cancel out. These are the same things. I can merge it into secant cubed. Okay, so there we have it. Instantaneous rate of change, that's the derivative. Average rate of change, that's the slope between the endpoints. And then if we were to solve for t, it would be another process I'm not going to ask you to do, but this is all it's asking for, to just set it up. Part C says, what is the instantaneous velocity at t equals pi seconds? Okay, what would you do here? Yeah, just plug pi into the what? Yeah, into f prime, right? F prime is the velocity function. Okay. So basically just finding f prime of pi. Yes, we can basically practice our unit circle knowledge here. So this is my derivative, right? I'm just going to plug pi in for the t's. Okay, if you think about the order pair at pi over 6, it's root 3 over 2, 1/2. Right. Secant is related to cosine. What's cosine of pi over 6? 3 over 2. So secant will just be what? Yeah, reciprocal. Yeah. Right. What's tangent of pi over 6? Yeah, pi over x, 1 over root 3. You know, the 2's just go away. I can just ignore the 2's there. 1 over root 3. Two cubed is 8. Root 3 cubed is just 3 root 3. All right, root 3 times root 3 times root 3, get 3 root 3. And I can multiply this further. Root 3 times root 3 is 3. 3 times 3 is 9. We're asking for the velocity here, so meters per second. Part D, we're just asking for instantaneous velocity at a different t value, so at 2 pi. So repeat the same process, just plug 2 pi instead of pi in for the t value. All right, 2 pi over 6, same thing as pi over 3, secant of pi over 3. Order pair at pi over 3 is 1/2, comma root 3 over 2. So secant of pi over 3 is related to cosine. Cosine is 1/2. So secant must be 2 over 1. What's tangent of pi over 3? Just root 3, right? Root 3 over 1 is just root 3. 2 cubed is 8. For E, write the equation of tangent line. There's more practice with unit circle here. Okay, we have the slope already, right? So just have to find the order pair. Again, secant the power over 3 will be 2. We already found f prime of 2 pi from earlier.
Consider this to be a bonus string.
Well, I'm not even going over it. Particle motion will be from like, when is the particle moving left, when's moving right? We won't do that. This is really just an application of mean value theorem and rules. It just has the wording of velocity, but really we just think of it as time. Okay, so just want to do a little bit more review with mean value theorem. Okay, let's turn to page 3. Bottom of page 3, number 4. Say basically implicit differentiation problem here. It says find the equation of tangent line. We're not going to do that. We're just going to find the derivative. Okay, so let's find the derivative. But we do see applications of implicit because we have y sticking out, and then also what else do you see on the right side here?
The y.
X squared times y. What's needed there? Implicit. Okay, what else? Particle, right? X squared times y, they're multiplied. Okay. So try that, see if we can, this is basically what what you were able to demonstrate on your quiz. So see how well we do. I'll walk us through it once you guys start working on it. So we're just going to find dy dx. We're not going to the whole order pairs. Okay, what's pi y's derivative? Pi dy dx, right? We see two y variables, so we're expecting two dy dx's to pop up in our derivative line. Factor dy dx out and bring everything over to the other side. Okay, check my work. Okay, you guys get the same thing. Okay, so this is a example of topic 2 that you might see on the test involving product rule and implicit and trig derivative rules. Everybody okay? Right, let's go to the top of page 3. I'm going to skip those 2 problems, but I want us to, we can cross off 1 and 2, and I want us to practice our inverse trig derivative rules, and then see if we can try find the derivative for number 2. Okay, remember, it's just these 3 rules that you have to really memorize, and then you can just copy the ones to the left and just put a negative in front. Remember, all the numerators are the same, and then all the denominators involve 1 and u squared. Start with the easiest one, go to the most complex, and then if you can figure out this arcsecant one, then arcsine will have a similar but different order of your 1 and u squared. Check their derivative rules. All the numerators have u prime. We start with the easiest one, the 1 plus u squared for the arctangent. And we can establish here that 1 and u squared will be involved with all your derivatives. Arcsecant, it's the most complex one. It's got the absolute value of u, but the u's are next to each other, so that helps remind me that under the square root, it's u squared minus 1 and not 1 minus u squared. And if I can figure out that order, then I can just take that, adapt it to arcsine, but then just swap the order around, make it 1 minus u squared. Okay, here's number 2. Arcsine and inverse of sine, these are the same rule, just different notation. So when you see that notation, it's not secant raised to -1. This is arcsecant. Okay. All right. What overarching rule do we have to make sure we involve here? Product rule. Good. All right. So f prime g plus f g prime. And then what's the rule for e to the u? Yeah, e to the u times u prime. Okay. All right, go ahead and try that.
Choose different way, you changed this.
I'm sorry?
You changed number 2, right?
I did, yeah, I changed number 2. And then you don't have to simplify. Once you get to product rule, you can stop. Okay. I'm not really simplifying here. I'm just rearranging it. Okay, let's see if we can finish off with a curve sketching problem. This is page 4, number 6. You can have your calculator out, so you can graph it and check your work. And the key is on page 10.
What page is this on?
Oh, this is page 4,
Page 4.
but the key is on page 10.
Okay. But you was more space on the test too.
I'll give you a full page, but you can always get more scratch sheet. Yeah, so never feel like you need. I'm gonna never feel like you're restricted with space.
The range can go up to 4 pi.
Mhm. Yeah, this is an instance where, I mean, you can tell by looking at the graph as well, that my slope is always going to be positive. But my concavity will alternate. I want to find my, there's no relative max, relative min, but if this is a relative max, relative min, I will plug this back into the original function, get that order pair. F double prime, 1 goes away to 0. Cosine becomes a negative sign. The two negatives cancel out. Yes.
Confused because I thought you said all the problems would alternate up to.
Yeah, this one is, I guess I just have to find more practice problems, but this one may not be fully representative of where you're going to see. And also you can tell by looking at your graph, right, that the slope is going to be always rising. But on the test, yeah, I'll be alternating.
Oh.
But the concavity will alternate here if you look at your graph. Okay, so sine of pi over 2 is positive, so that's concave up. Sine of 3 pi over 2 is negative, concave down. 5 pi over 2, if I subtract 2 pi, that's same thing as pi over 2. So sine of 5 pi over 2 is same thing as sine of pi over 2, which is positive. 7 pi over 2, sine of 7 pi over 2 is same thing as sine of 3 pi over 2, negative. So even though there's no relative max, relative min, we do have points of inflection still on our graph. You can find those points by inserting back into the original function. Let's also plot our order pair for endpoints. So the graph is going to, it's just going to rise, right? It's not going to, no relative max, relative min. So we know the path of the graph is going to be rising the whole way through, but we can put curvature features into it after we plot our points of inflection. There's order pair at pi, comma pi. There's order pair at 2 pi, comma 2 pi. There's order pair at 3 pi, comma 3 pi. And we give it the curvature based off of our concavity sine line, right? We start off with concave up, then concave down, then concave up, then concave down. So concave up, concave down, concave up, concave down. Okay, we'll continue one more day of review tomorrow. All right, come get your phones.
Hey, go get a password from us. Did you all have the characteristics, Mr.
I did not. Yeah, so you can just look on page 10 for all the characteristics. Yes.
Checked it too, 0%. It was from called the exact same song.